Welcome, or hopefully welcome back to the Reliability Matters podcast. For those of you who are counting, this is episode number 154. On today's episode, we're going to dive into the most critical aspects of manufacturing high reliability circuit assemblies, thermal profiling during the reflow process. Whether you're designing, engineering, or troubleshooting circuit assemblies, understanding how temperatures during the reflow process influence the quality and performance of your assemblies is essential. In this episode, we'll break down what thermal profiling is, why it's important, and how it affects everything from solder joint integrity to component placement. We'll also explore the challenges and solutions involved in getting your thermal profile just right, ensuring your circuit assemblies are built to last in a competitive and defining industry. We'll review thermal profiling best practices, common mistakes, and various capabilities of thermal profilers. My guest today is Mark Waterman. Mark is the Electronics Division Manager at ECD, a manufacturer of profiling equipment founded in 1964. Mark began his career at ECD in 2006. I'll ask Mark all about thermal profiling best practices right after this. Stick around.
Welcome to Reliability Matters, a podcast for the electronic assembly industry. Each episode covers topics related to reliability, best practices, and environmentally responsible assembly techniques, with insights from experts across the electronic assembly industry. Now, here's your host, Mike Conrad.
Hey, Mark. Good to see you.
Hey, good morning, Mike. Good to be here.
How you been?
Good.
I understand you just made a major move, geographic move, right? You're in Texas now?
Yeah, we moved from Oregon, the headquarters for ECD, out to a suburb of Dallas, Texas. So I don't think you could get a more different place to come to.
I was going to say, it reminds
Oregon.
me of the line out of Wizard of Oz. You know, we're not in Kansas anymore. You're not in Oregon anymore.
Right.
Well, I live in California, and I think half the state has already moved to Texas. So I think Texas probably isn't Texas anymore. It's now a homogenous combination of Western states people. You know, California, Washington, Oregon. It'll be interesting to see how that affects Texas. But well, thanks for agreeing to do the show. I appreciate it. It's good to see you again. And just a heads up for my audience, Mark, probably just slightly out of the camera frame, is maybe a second guest who might make a surprise appearance, and that's Heimdall, which is Mark's dog. Mark's dog is anxious to get his SAG card and come on camera and get famous. So. I'm not sure what will be the bigger takeaway, Mark's handsome face or the dog. We'll see. But
that's right. The dog's definitely more handsome. But,
aren't they all? Yeah. So I feel the same with my dog. So Mark, ECD, Electronic Controls Design, I think is that's the long version of that acronym, has been around. I was 4 years old when it was established. I believe it was established in 1964. We didn't have reflow ovens that I know of in 1964. There were no surface mount components in 1964. There were probably wave solder machines or drag solder, dip solder machines back then. Did ECD start off with thermal profiling, or did it kind of morph into that?
No, it was definitely an evolution. It got started actually before 1964 as the Thought and Thing Factory from our founder, who wanted to engineer and make different types of controls, from everything from cherry pickers to, industrial lighting. And then we got into doing contract manufacturing, assembling artificial kidney machines, of all things. And so from that assembly side, there was a strive or an initiative for quality. And so we did everything backwards, right? We had problems with our quality of our circuit boards, so we decided to bring it
Make 'em
in-house
yourself.
and make them ourselves, right? We had problems with contract manufacturers assembling the boards, so we brought it in-house and made our own contract manufacturing business for the circuit board assembly. And
Something
out of
tells
the
me you had a
need,
profiling problem one day, or you had a temperature
yeah,
problem, right?
yeah, as they say, necessity is a mother, right? When we had a need and we saw the gap, and from that unique insight of being in the manufacturing industry, we designed tools to help us solve our own problems first. And it includes, we were dabbled in washers for a while. We had, flux density controllers, did all types of different kinds of equipment. And as these divisions grew, like our circuit board manufacturing, we spun those off and sold them off. Contract manufacturing the same way. And those to this day are still successful businesses that continue on. And then the core of the business was really the profilers and the electronic metrology side, doing things for contract manufacturers. And that's what the core of the business is now, and what we've been for the last 30 years or so.
Do you consider yourself a software company or a hardware company?
Boy, I wish I knew the answer to that.
I'm sure it depends on the day, right?
And it depends on, what projects you're currently working on. We are really a hybrid. We're both. The profilers, there is a certain amount of intricacy and expertise that goes into designing something that records temperature through a thermal process. But I think maybe where more of the expertise lies is how do we do the analytics on that data collection? How do we interpret it? And more importantly, how do we display it to the end user in a way that's digestible?
Right.
So we really are both a hardware and a software company.
Yeah. And we'll get more into that. I think I probably asked that question a little prematurely, because I do have some software and hardware questions coming up later, but just to kind of prime our audience here. So most of my audience is in the electronic assembly space, but not exclusively. So let's just kind of start with a 30,000-foot view here. What are the key factors companies should consider? Well, no, let me just ask you an even more rudimentary question. Explain to me and my audience what, in the context of electronic assembly, what profilers are, what their purpose is, and why one would even consider using a temperature profiler, since the ovens already tell you what temperature all the settings are at. Where does this value-added component come in?
So I guess we need to define what a profile is first and foremost, and that is the graphical representation of a temperature over time plot. And so that creates a unique shape based on the process that you're doing. When we look at reflow and electronics soldering a circuit board, we're measuring how we heat up the components and the circuit board itself to get those solder joints up to a temperature that the solder turns liquidous and forms a solder joint. And then we cool it down to a solid again and actually form the solder joint. That profile, that thermal excursion, is what our profilers measure. And we say a profiler generically to represent that graphical plot of temperature over time. Now, you could use any kind of data acquisition device that would measure temperature and use very long thermocouples and attach them to very delicate, intricate parts of your circuit board, then carefully string those through the oven for 16, 18 feet through the reflow process, and then quickly pull it back through what we call feed and retrieve or fishing method. And that's cumbersome at best. It oftentimes affects the process because the wires, as they get dragged through, can cause the board to move inside the oven. You've got to have very long wires, which introduce electrical noise and air into the process. So the need to have a traveling profiler that travels with the product in relatively close proximity to the board and be able to go through the process is kind of our claim to fame, right? We put the data logger into a protective cover. We have the sensors coming out of that attached to the board, and it travels with the product through the process. Makes it much more effective, easy to collect that data instead of having very long trailing, thermocouples. It's more accurate, more convenient. It's just a better way to do it.
So you have a circuit assembly, which is a measurement device that has thermocouples attached to it and memory and software on it. And this circuit assembly is going through a reflow oven, not for the purpose of being reflowed. So you have to insulate this circuit assembly and all the components on it so that it doesn't reflow every time it goes through. Do you, just out of morbid curiosity, do you when you build those boards, do you use higher temperature solders, or do you just do a really good job at insulating, thermally insulating, so that it doesn't get exposed to reflowable temperatures?
The answer is a little bit of both. So we try to source components that are what are considered automotive grades, so they're good to a little bit higher temperature than standard electronics. We use a standard SAC 305 solder because we want to stay RoHS compliant, just like the customers that have to build their assemblies do. And then we do try to give it more insulation than is needed to keep it at room temperature. I mean, the electronics themselves is no more resilient to temperature than your cell phone. And at the price we charge for it, we want to protect it, make sure that it doesn't get damaged. And we think we do a pretty good job. Unfortunately, maybe too good of a job, because they tend to last longer than we'd like them to.
No planned obsolescence here, right?
yeah, exactly. We have instruments that are 20 years old and still going strong. So that's a testament to their longevity, I guess, and the effectiveness of the design.
Well, I suppose what keeps products turning over is the potential obsolescence of the software that's running on it, right? Because even though software can always be upgraded, it can't always be upgraded with the component set that is on a particular assembly. So we know that with computers, with I'm staring at a laptop right now, and that laptop gets updates every few months from Apple, and at some point, the latest and greatest doesn't work on this hardware anymore, right? So I'm sure that, a 20-year-old profiler is probably not running the most current, modern, feature-equipped software that is available.
Yeah, and that's for us as the manufacturer as well. Is component obsolescence is a real issue because sourcing, compatible chips oftentimes just isn't viable, right? You can't get a 1 megabyte memory chip anymore, right? They stopped making those 20 years ago.
Right.
So
we've had that problem in our equipment manufacturing process, not just components, but LCD screens, monitors. We used to have this nice little monitor, and all of a sudden, those little monitors are 5 times the price of a monitor 3 times the size, right? Because there's this sweet spot in consumer electronics that you kind of like to be in when you can. All right, enough of the nuances of two manufacturers talking to each other here. What are the common challenges that companies like yours face that your customers face while setting up an accurate thermal profile on a complex PCB? I know that there could be some density issues. It could be some ground planes. It could be, different thermal masses, but there's probably more than that. So what are some of the gotchas and some of the challenges that have to be overcome when figuring out where and how to measure certain parts of a board?
Well, what we're seeing recently in the last couple of years is that there is a huge disparity in mass. And so you have a 2-inch BGA right alongside some 0402 that can't be heated up over 250 degrees. and that we're right on the very edge of where convection reflow ovens can effectively solder some of these assemblies. So we're getting more and more calls from our customers saying, hey, I've got this impossible process on this impossible assembly. How do I make it work? And sometimes the answer is it's not going to work. We're waiting for solder paste manufacturers to come out with long life fluxes that can, be active for these longer heating periods. The convection rates that regular convection ovens can provide is like say right on the hairy edge of what's needed for some of these assemblies. So we see vapor phase getting some favor in large heavy assemblies, and we see new technology with smaller components and higher density, like say in ground planes, 5G, 6G boards, where they are designed to dissipate heat and to resist being heated. So they are also making it very difficult for our manufacturers to get into a process where they are not damaging components, they're abiding by the solder paste recommendations, and still getting the silly solder to melt. It's a tightrope out there. And always an issue is the skill resources available to a manufacturer. Does he have a process engineer that can spend time to go out and make a unique recipe and profile and assembly to get the perfect process down? There's a lack of some of that expertise, or that expertise is being allocated to other higher value jobs or activities. So that's another stumbling point. And then having the actual assembly to profile. If you've got a $10,000 board, the customer says, I'm going to give you parts for 20 boards, and I expect 20 boards back. And
right, not 19.
Yeah, and they all better work, right? So the manufacturer is in a really difficult position, and sometimes not using best practices to get them to over the goal line, so to speak.
How much, based on your experience, how much of setting up a profiler on an assembly is black and white science, and how much of it is black art, right? Tribal. Is it 50-50? Is it 90-10? What do you think?
It's a loaded question. So if you're at Intel, they probably have a procedure of all the points.
Very black and white at that point.
Yeah, and there's no ambiguity. But I think probably in more manufacturing houses than not, it's a little mystical arts, right? Mm-hmm. And I think this, and it goes back to the liability of the cost of the assembly.
Sure.
If you're making some, fast food toys for a Happy Meal, there's much less liability if it doesn't work in the end. Right. Whereas if you're making, thrusters for, a Boeing Starship, there might be a higher level of quality needed for that.
Well, there's a topical example, right?
Yeah, exactly.
The Starship's back down, but the astronauts are still stuck in space.
Yeah, exactly.
Yeah, that's a strange one. Everything is in your world is based off of thermocouple measurements. And I know that I'm not an expert in any way on thermocouples. But we do use some in the equipment we manufacture. I think we use, I want to say K-type thermocouples.
Correct.
But how important is it to select the appropriate thermocouple? What are the variances and variables in thermocouples, and what would drive someone from a K-type to a J-type, if there's a J-type, to any other type? Are there advantages and technical limitations of certain types of thermocouples?
No, absolutely. So K-type is wildly popular, and that's because it's cheap for the most part. it's fairly accurate over a large temperature range, and it's good for probably 90% of what you're measuring in electronics. There are some special types out there for exotic applications like cryogenics. Some thermocouples have a higher accuracy at lower temperatures, and you may want to choose those types if you're doing cryogenic type of measurements. There are also some types that if you're doing very high temperature or in very demanding environments, oxidizing environments, or different types of chemicals, that you may want some of the exotic thermocouples that can last for a long time. You start getting into different alloys that are exotic and expensive. But type K, it's chromolumal and nickel. Fairly accurate, 1 degree C with special limits of error. Easily the cheapest thermocouple available, and good from minus 100 to 1,000 degrees, so a wide temperature range, and a fairly straight electromotive force curve. I'm going to get too technical here. But if you're doing just standard temperature measurement, type K thermocouple is probably going to be what you use. And if you're measuring processes below 500 degrees C, there's likely little to no drift over time. When you get into control applications and high temperature furnaces and stuff, you have to worry about thermocouple drift.
Well, I would think in our world, if we got to temperatures over 500 degrees C, accurate profiles would be the last of our concerns.
Yeah, exactly. Materials. So funny side story is that we have a customer that's in a clean room environment doing an application at 370 degrees C, which seems like, that's not that far off from, 300 or 280 or, we're only talking 100 degrees difference. But that jump in materials between a 300 or 280 degrees C material to a 380 degree material, it's an ocean. You just can't get there from here. And so there's even 100 degrees difference can make a huge difference in what you can actually use in materials. That's a side conversation, but interesting nonetheless.
So most of us mere mortals who are putting circuit boards together, who are assembling circuit boards, most of us are going to be in the K-type thermocouple range, it sounds like.
No, absolutely. That, like say, that's why it's the de facto standard for temperature measurement.
Yeah, and that's what we use because it was, we're measuring temperatures well within its capabilities. So if we were to ever exceed those capabilities, we have bigger problems, as I alluded to earlier.
Right. The one thing I'll add is the insulation material for the thermocouple. So type K is the alloy of the wire that actually forms the junction and right. measures the temperature. But the insulation also has to be temperature rated. PFA or Teflon insulation is fantastic. It's wear resistant, but it only goes to about 260 degrees C before it liquefies. Once it liquefies, it actually will contaminate the measurement that we're getting electrically from the thermocouple. And so oftentimes you'll see some weird noise in a temperature profile up at the peak temperature, and it's because that Teflon is starting to liquefy.
Does it have a physical appearance when that happens? I mean, can you look at it and say it's damaged, or is it more subtle than that, more internal?
No, it's more subtle. It doesn't actually get damaged. It just partially liquefies. It'll get clear, and then as soon as it cools down, it will go back to its normal color. And
so it leaves no trail behind. There's no evidence.
It leaves
no smoking gun.
The electrical interference is what it leaves behind.
That's the tell. So how?
Go ahead.
How does one determine the number of thermocouples that should be put on an assembly? If an assembly, if the density of components and the thermal mass is pretty consistent, I'm assuming maybe fewer thermocouples would be needed. If does a varying density and thermal mass mandate more thermocouples? Are there other criteria that would lead you, as a manufacturer, to recommend more thermocouple measurements on a particular assembly?
So, again, a nuance here is that what we really need to measure on a board is the hottest spot on the board, or the hottest component, the coldest spot, and maybe anything that was heat sensitive. So even if you had a huge, massive board that had a huge BGA and a little tiny 402, technically with 3 thermocouples, if you got the hottest, coldest, and the most sensitive, you're getting all the information you need from that board, because everything else will fall in between. Then the question becomes, how do you know that place is the hottest? How do you know that place is the coldest? And you do that through NPI or discovery. And that's when you need to get a lot of thermal data from a lot of different points, so that you can prove out that that board that you are measuring the hottest point on that board, or the coldest spot. So if you have more complexity, that's more spots to measure. And less complexity means fewer spots to measure. But if you get the 3, then everything else will fall in between.
It's like Goldilocks. The porridge is too cold, too hot, or just right? You want to see both ends of the spectrum. Your company and others have been making profilers for a number of years. It's not a new technology. What have some of, in your perspective, you started at ECD in 2006, and I think, and so you've seen some change, and you've heard of some change, from times before you. What, in your opinion, would be some of the more significant advancements that have been made in profiling equipment over the years that really land on assemblers?
I'm going to be incredibly biased here because, of course, my products.
Of course, yes.
But if we look back in maybe the last 15, 20 years, the software tools that are available have improved dramatically. The features that are available to either analyze or to help predict or refine the profile itself, I think have improved greatly. But the most significant change has really been with our touchscreen interactive display. So now we've untethered our profiler from the computer. We're able to configure it on the fly on the factory floor. We're able to collect the data and analyze it right on the profiler itself. And we're not tied to that software that's on a PC that's maybe on a desk in your office or on a piece of equipment, which I think is probably the most significant innovation.
So the profiler itself is the computer, right? You're basically taking what used to be on a PC, on a workstation, you're basically putting that in a thermal box and running that whole thing through an oven, in essence.
No, absolutely. And that's, technology has allowed us to do that with the increases in memory and CPU speed. And, we can fit all that into a handheld device now and be able to bring that data and functionality into your hand instead of at a computer terminal.
Yeah, interesting. So one can take a box that goes through your oven, and what do they do? Plug a monitor into that box, or does it transmit the data to a workstation, to a laptop? I mean, how does one interpret the data once it's recorded by the box? How does it get to someone's eyes?
Yeah, so we have a discrete. It's a 200 by 400 LCD screen that's built into the profiler itself.
You're sending display screens through ovens.
Yeah, absolutely.
That's amazing. That's amazing. You guys just ought to have a company that just, builds thermal enclosures for people, because that's a challenge. I understand maybe it's some boards going through, but to be functioning while they go through, and to have devices on them that would be considered, very fragile, like these display screens is impressive.
Yeah, that's there were people that didn't think it was a good idea, so there was some pushback. Which whenever you innovate, there's always risk involved. But we tried to mitigate that risk as much as possible. We said, hey, if you drop this and break the screen, we still need this to be a mold. we still need this to be a profiler. So we created the firmware so the display can be on fire and it will still record temperature. And what if we get it overheated and it totally goes blank? It still acts like a mole. So, or temperature logger. Sorry, I don't mean to be branding here, but so a lot of thought went into that risk mitigation because we were doing something that had never been done before. And we knew that there was going to be pushback. But the same is true with the lithium ion batteries. Battery technology, great energy density, small size, but it is a little thermally sensitive compared to other technologies.
Sure.
But there is a trade-off, and as long as you mitigate that risk, we get to do fun and exciting things, right?
Yeah, absolutely. So if I wanted to buy a profiler and I know nothing about profilers other than kind of what they do, what are the most important specifications to look for in a thermal profiler? What if I Mark, I need a profiler? What kind of questions would you ask me so that I would not overbuy, underbuy, if there is the possibility of doing that? The most appropriate controller for my needs today, and maybe a little bit of runway in case our needs change.
Right. So that's a very personal question. I'll tell you, our company is a Cadillac product, and my mom always say, never be afraid to buy the best because you'll never be disappointed. But the best isn't always needed, as you state. Sometimes you're a small contract manufacturer. You don't even have a profiler on the floor, except for maybe something built into a machine. You want to get to your first step. The things that are important are the number of channels. How many thermocouples am I going to read per run? If I have a 4-channel unit and I need to measure 20 spaces, it's going to take me 5 runs through the oven to get all 20. So that has to be taken into account. The cost benefit of fewer channels is usually cheaper, but it means more work for me on the backside. It can still perform all the same tasks that an expensive one can, but it takes more human labor. The software that comes along with it, does it have the features that your company needs today and into the future? Are you primarily looking at this for labor savings, for documentation, for process development? So you need to analyze the software and make sure it meets the needs for what you're doing. And again, you get what you pay for. Data loggers can come in all shapes and sizes. If you've got a very large opening and you can put it in a big giant box and run it through your process, you probably don't need as an expensive logger because you pay a premium for size, for the analytical software, and for the customer service. Do you expect free software updates for life? If you have a problem and you call the company, is somebody going to answer the phone? Are they going to return your email? So there are intangibles to that as well. But number of channels, maybe accuracy. If you have a very dependent process where 5 degrees might make a difference, you should look at the accuracy of your profiler and not. You got to watch the fine print on some of these because they'll claim an accuracy with a special, I'm making air quotes here, special calibration that's never practically achievable in the field. So make sure you read the fine print on some of those.
Sure.
But sometimes your process doesn't need to be accurate down to 1 or 2 degrees. You've got a big window and non-complex assemblies, and you just need to prove to your customer that you're not burning things up.
And speaking of calibration, do these devices require calibration? If so, what's the process like, generally speaking, and how often should one calibrate the devices?
So calibration, especially in the old days, was meant to negate small drifts in components, right? You had, paper resistors and you would get drift organically over time just because of the materials that these components were made out of. So they constantly needed adjustment to bring them into tolerance. As things became solid state, that need for adjustment is really not there. All of our instruments that we produce anyway are fantastically stable and rarely, if ever, need adjustment. So calibration becomes an exercise in documentation and liability again. So we recommend, as the OEM, a 1-year interval between checks to see if it's still right. And that's kind of the industry standard. If you had maybe a medical application and high liability, you may want to go to a 6-month interval. If you're making, curing paint on a barbecue, maybe 2 years is enough for you. And again, it's just a piece of paper saying that it was accurate that instant that it was checked. It doesn't promise that it's accurate tomorrow.
Right.
And it doesn't say that it was accurate yesterday.
Right. It's accurate at that moment. And who performs that? Are calibration tests performed by the customer? Do they send it into the manufacturer? Do they use an independent lab? What's the process?
So it varies between customers. Some have their own in-house metrology, and they're as qualified as they want to be to provide those self-calibrations. At ECD, we're an ISO 17025 accredited lab, which is similar to other ISO. We have to have a quality manual and follow the procedures. With the lab certification, it's not only do we say we're doing everything right, but are we qualified to do it? So we have to have a little higher level of proof that we're qualified to produce and perform those calibrations. And in that sense, too, any ISO 17025 accredited lab would be qualified to perform that calibration. So we just ask that you make sure you're using an accredited lab. We don't have a proprietary process or require people to use us as the calibration house, although oftentimes they do, because we offer some other value-added activities.
Sure.
Along with that.
Yeah. Put a bow on it and make it a little bit more attractive.
Yeah, exactly. Yeah, we're the OEM, so we can update the firmware and replace the batteries if they need it, etc.
You mentioned earlier data logging. What role does data logging capabilities play in the selection process of thermal profilers? And how do you use this data for long-term process optimization?
So two things when we talk about data logging. When we talk about the profiler, that's the log interval, or time resolution that you'd have. So you need to make sure that
taking
you're using
a recording every second or every few seconds or every millisecond. Is that what you mean by timing?
Correct. So if you're doing a wave solder process and the important part happens in 5 seconds, you want to have more data points in that 5 seconds by using a faster logging interval. If you're doing maybe a 5-minute reflow process, once a second is fine. If you're doing a curing application that might last a half an hour, you could probably log it once every 10 seconds. So having an adjustable log interval is nice, and you need a time resolution that makes sense. You don't want to log every 10 seconds on wave solder because you'd miss the event, right?
Right. Yeah. Right. You'd be over the wave before it even took a picture of it.
Now, what we do over time with that data and with profiling in general is, and I think what you're aiming for was the statistical process control and process improvement or process stability. So when we collect that data, if we collect the same data over time, over and over again, we can use that to show process stability. And if we see process drift, we can use it as a red flag to perform maintenance or to do adjustments on the process to bring it back into control. And that's a huge value that measuring a process brings. We say you have to measure it to manage it. If you're not measuring some of your processes, you won't know when it's drifting. And you have an assembly that passed tests last time we ran it, and it doesn't this time. What happened in between?
Yeah.
And so data gives you that power, and these days it's artificial intelligence and machine learning, and those are really fun buzzwords, but it comes from collecting data and doing statistical process control with it.
Just interpreting the data, discerning the data, right? Not just it stopped working one day. There's usually a progression toward toward that. Is it possible to use products like yours to predict how to set a reflow oven? Are there tools that allow you to go into software, profiling software, and say, this is the profile I want to see, and then it says, okay, set zone 1 to this, zone 2 to that, zone 7 to that, et cetera. Like prediction software, things like that. Is that
absolutely
part of it?
So, and that's what we talked about with the software component and meeting the needs of the customer, is that a large portion of the value of the software is being able to save time by using an accurate prediction model. And when we measure something with thermocouples on it going through a process, we can very accurately, through data analysis, see how that product was affected by the set points of the current set points of the oven. And then we can very accurately predict how changing those set points will affect that product temperature. So that is a huge benefit to the software itself, and one of the selling points. And ourselves as well as our competitors have different flavors of that prediction model and what you can do from their software. And so it's important to bring that up and to analyze each one and how it might best affect your process. ECD in general is a little more hands-off. We like an engineer or process owner to make decisions about where they want the process to be, and we let them steer that prediction. Others may step in and have an easy button that kind of make decisions for you, but it's only easy if it's right. So
true. Yeah, very true. I can think of a number of examples in software where I use Photoshop a lot, and Photoshop has, two ways to do the same thing. One is to force it through, a lot of detailed work and, stuff like that. And then the other is, you can press a magic button, an easy button, and it'll be done for you. And I'd say probably 85% of the time the easy button works, and 15% of the time it's disappointing, and I have to go back and do what I wanted the long way. So it's probably the same in your world too, right? Or worlds where they have an easy button.
And it's like the magic wand tool, right? If you know how to set the tolerance band, you can usually get there using the easy button.
Exactly.
So those same types of tools are where the software brings value in. And we're in the throes of developing our new replacement software right now, and building in value by tools that make it easier is definitely the key goal, as well as visualization. Tastes for the way things look change over time, and ECD's been very good at keeping our software familiar to maybe our longtime users, but familiar to longtime users looks old to new users.
Right. Well, sometimes software companies change the interface just to change the interface. Behind that, it's kind of the same, and that drives me crazy. It's like I want more functionality. I want more accuracy. I don't necessarily need a new user experience, because when you do a user experience, that sometimes masks the fact that there's nothing new behind it, except the icons are in a different place, or there's a different, emoji somewhere, right? It's you kind of want more of the meat and less of the aroma, right?
Yeah, exactly. I have to admit that I actually would like to see a curmudgeon mode where it looks exactly the same.
Curmudgeon mode. I like that. Yeah. No easy button, but we have a curmudgeon mode.
That's right.
Yeah, you're right. A lot of times like on Outlook, for example, I use Outlook for Mac. A few years ago, they upgraded Outlook, and they actually put a little toggle switch where you can toggle between the new Outlook and the old Outlook. And I did that a couple of times, and I'm like, I'm not going with the new one. I don't know if the new one's better or worse, but I know where everything is. And they just move stuff around just for the sake of moving stuff around to prove that something changed. As we're kind of running out of time, I want to get a couple more questions in. What are the I always like to ask what I like to refer to as stupid people tricks, right? So I'm not saying customers are stupid. I make stupid people tricks all the time. What are some of the most common mistakes made with thermal profilers? Either the most common mistakes and or the most common misconceptions about profilers?
Well, I think a key misconception is that you can profile a bare solder sample board with no components on it, and it provides you with anything useful.
Someone's trying to save some money and not put a bunch of components on it, right?
Yeah, exactly. At the very minimum, try to get a board that has similar components from your scrap pile, or glue down some old components on a similar board. You're going to get more viable data than you would by just running a bare solder sample through. Thermocouple attachment, always a semi-contentious issue.
Do not tape them down with Kapton tape. I remember hearing that. I think I may have heard that from you.
That's right.
But Kapton tape is not a good bond. Is that correct?
Correct. Yeah, it's great for strain relief, but terrible for attaching thermocouples. You can have success with aluminum tapes and the window painting method. It does take time. Anything that is done well takes time. We advocate for high temperature solder, which makes repeatable, thermally intimate connection.
I wanted to ask you about that. I've heard about soldering it on. The tip of the thermocouple is soldered together, right? There's two wires that are soldered together at the end. Welded together at the end. So soldering over the weld doesn't change any of the measurement characteristics or anything, because you're applying another metal to the tip of it. Does that change anything? Apparently not.
So the short answer is no, and that's because the blob of metal, as the wires come in, the solder becomes the thermocouple junction, and the temperature of that solder ball that you use to attach it is what's being measured. Mm-hmm. And the ball, the weld, that bead on the end, in essence, is just an anchor so it doesn't pull out of the solder. If we could keep the wires in there without the weld, it would be just as effective.
Okay.
If you're using high temp solder, and of course we want to have the least influence on the measurement itself. So using the least amount of volume, the smallest thermocouple bead, because we can have problems, especially as you get into larger gauges, is that it will actually collect heat and put heat into the joint and alter the measurement. So you have to be aware.
Heat sinks a little bit then, because there's a little bit of a thermal mass, right?
And it acts like a little sail. It collects heat and pushes it into a very tiny joint sometimes. So that has to be understood.
Are there adhesives that work well?
There are SMT adhesives. They tend, all the epoxy-based adhesives that are out there tend to give up at about 250 C. And so you're right in that weird range where the material is about ready to fail. So if you thermocycle it one or two times, it starts getting micro fractures in it, and the temperatures will slowly rise over time every time you run it. So it's not as repeatable. And like I say, you can have good success with aluminum tapes. They're semi-repeatable if you don't have to do multiple runs, and you take the time to do it correctly. But you want to have something that's thermally intimate and then doesn't affect the measurement. That's the goal.
Is there such thing of a circuit board designed with thermocouples kind of embedded in it that allow, in strategic places like under a BGA, something that you really can't get to otherwise, that maybe have an edge connector at the end or something that a profiler can log into.
There are designs for that with both embedded RTDs and with thermocouples. They are very special use, and the expense tends to shy people away from them.
Okay.
Because it's a special alloy that they've got to embed into the circuit board itself.
Yeah, but otherwise it would otherwise be foreign to the board, right? There was no reason for that type of alloy except for
temperature measurement,
recording temperatures. Yeah.
So it has been done, but they are very special use kind of applications. Other misconceptions that we run into all the time is the way the thermal barrier works. And I've equated this in a couple different ways. You can tell me which one makes more sense to you, but the insulation, when we put a barrier around it, is just a thermal resistor. It slows down how fast the heat can penetrate. And we give it enough resistance so that it takes more than 10 minutes to go from the outside to the inside. But if you don't let it cool down between runs, that 10 minutes doesn't just disappear.
Well, I would assume that if you don't give it enough time, it now has a 6-minute resistance. And then if you don't give it enough time, it has a 2-minute resistance, right? So at some point,
correct,
you're not starting from the same point.
Right? Exactly. And the other analogy I use is holding a sponge over your head in the rain, right? That sponge is going to collect the rain for a while.
Yeah.
And you're going to stay dry, but at some point it'll become saturated, and every drop that hits on the top there's going to be a drop that comes out the bottom. So you reach a point where it becomes ineffective if you don't dry it out between rainstorms.
What's on average? 10 minutes, 15 minutes, 30 minutes, an hour? What's the average kind of time to come back to ambient or close to ambient?
It depends on the material and the barrier itself. We have, for every application and duration and temperature, we have a different amount of insulation that we need. And when we get into long durations, we use special heat sinks that are phase change materials. So we have barriers that can go at 900 degrees C for 24 hours. You need a wheelbarrow to move them around, but and those take literally 24 hours to 18 hours to cool back down again.
Right. You can't just throw it in a fridge because then you get thermal shock stuff, right? So
yeah, exactly. And it holds a lot of heat energy, and so it takes a lot of time to dissipate all that heat energy.
It's interesting. I never thought about that. I thought that they were all just repelling the heat instantly and they were coming out, cool to the touch, but that's not the case.
Yeah, exactly. And that's the misconception, is that it doesn't reflect anything unless you're in IR. It can't reflect that heat away. That heat energy is around and it's being absorbed by the barrier.
Yeah, sure. Last question, get out your crystal ball, and it's fortune telling time. What would you consider the most important recent innovation in thermal profiling, and what do you think the future innovations will be? Maybe that's AI, maybe that's other measurement techniques or whatever, but what excites you today, and what are you looking forward to tomorrow?
So again, incredibly biased. The touchscreen display and having data at your fingertips, I think, is going to become the trend. Every profiler company is going to have to do that to just keep up with customer expectations. We know that ovens are becoming more sophisticated. There's more calls for that easy button to make profiling easier, or to process your circuit boards easier. And so I think there's going to be more automation and closed loop control. Probably, I don't know how the strategic partnerships are going to line up. There's been some movement in the recent times where, like I say, we have some of our oven manufacturers that are coming out with their own profilers. We're kind of playing in each other's sandboxes with continuous monitoring to a degree. And so it has yet to be determined where that's going to shake out with innovation and what the customers really want. We've always been a third party validation for your process, and we are reluctant to take control of an oven. We think the oven manufacturers are perfectly capable of controlling their ovens and doing a fine job of it. We want to be the third party auditor, the measurement company, not the control company, so to speak, even though it's in our name.
Well, I'm a big fan of the "you've got one job" philosophy, right? And as companies start expanding into what would be traditionally third-party applications, and they try and bring it in-house, there are very few examples of companies that have done that well, right? There's because they don't have the history, they don't have the tribal knowledge, they don't have the gut that steers a company like yours or others in your field that have learned through trials and tribulations, the best practices and things like that. They're looking at a product today, not really with all of the history that led to the decisions up to that day. So they may be able to mimic what is currently out there. The question would be, they didn't start from a trajectory, right? They're starting at one point in time, and that's hard to build a trajectory on. So, well, I don't know. It's going to be interesting to see. But I've often wondered why the oven companies didn't just do what you were doing and take over the whole third party thing. And my guess, up to after all these years, with still having third party companies as the majority manufacturer of your types of products, my guess is they just haven't been able to do it well, and they stay in their lane. And
there's a 3-year roadmap that's really easy to do on maybe a simpler device, but when you have a whole product portfolio,
right,
complementary products to go with it, we have to look at an 8-10-year roadmap.
Right.
And be very strategic and like say that crystal ball comes in more often than we'd like on where the industry is going. So part of that is easy. Doing one part of what we do, they might be able to be successful with it. But I don't think they'll ever get to the level of what the customer expects from a profiling company.
Sure.
To do. And that's where, like say, we are bespoke to kind of a single application or a single industry. And so we're able to offer a complete suite of products where, a single solution provider probably won't meet all the needs.
Yeah. Yeah, I think you're right. That seems very logical to me, but we'll see. We'll see if the crystal balls are accurate, right?
Yeah, exactly.
Mark Waterman, ECD, thank you so much for being my guest today. I really appreciate your insight and your wisdom on the subject of thermal profiling and crystal balls, and I really appreciate it. And your dog stayed stayed completely out of the picture.
It's totally out of character for him.
He gave up on his movie star career here. So this was his moment, and he blew it. Not getting a SAG card today. So
that's right.
And for my audience, if you'd like to get a hold of Mark, I will put his contact information, email address in the show notes. So if you're listening to this on your favorite podcast app, just go to the podcast app, look at the show notes, and Mark's information will be there. If you're watching this on the Reliability Matters YouTube channel, just right down here somewhere, there's a More button, click More, and Mark's information will be there. Mark, thank you so much for being my guest today. I really appreciate it. It's always good to talk to you.
Yep. Thanks for the invitation, Mike. It's always a pleasure.
My pleasure. Well, that's another episode. Thanks for listening to or watching the Reliability Matters podcast. Don't miss an episode. Subscribe to Reliability Matters on your favorite podcast app. If you're watching this podcast on the Reliability Matters YouTube channel, be sure to like and subscribe to the podcast to be notified when new episodes are released. We release new episodes on the second and fourth Tuesday of every month. A special thanks to the Printed Circuit Engineering Association's PCB Chat at pcbchat.com and Ascendo Reliability at reliability.fm for syndicating this show. Thanks for your questions and episode suggestions. Please keep them coming. I love to hear from you. Send comments or episode suggestions to Mike at mikeconrad.com. Just remember, that's Conrad with a K. To learn more about the podcast, please visit our website at reliabilitymatterspodcast.com. Once again, thanks for listening or watching. Until next time, stay safe, stay healthy, stay happy, and perhaps most importantly, keep doing it right. I'll see you again in 2 weeks.
Thanks for listening to the Reliability Matters podcast. Join us on the second and fourth Tuesday of each month for new episodes of Reliability Matters.